Welcome to lecture 32. So today I am going to discuss one of the most important topic of this subject, digital communication. Actually, not only digital communication, it is important in analog communication as well. However, this subject itself is extremely vast. We don't have enough time to discuss all nuances. But in this one lecture, I will just show the background and show the trajectory of the development of carrier and phase recovery, and I'll tell you that where it is leading if you want to really know more about this particular topic. So the problem of carrier and phase recovery, it is evident from any analog or digital communication system. Suppose let us take some DSB SC analog communication system. So over there, you know that the baseband signal is some XT, and what you are doing, okay, not XT, let us write UT or something like that, something else, yeah, UT. So what you are doing in that DSB SC, you are basically multiplying with the I to pi FCT, where FC is at a much higher frequency compared to the bandwidth of UT, and then you put some real of that, so such that your corresponding XT, which is going to the channel, so this is your channel, so your XT can be written as real of UT e to the power I 2 pi FCT. So to have a coherent detection, what you have to do over there, coherent say demodulation we can say. So what you have to do, you have to multiply this signal with the same waveform e to the power, say e to the power minus I 2 pi FCT, and then you have to do low pass filtering. So if you do low pass filtering, you will get back UT. That is the idea. If there is no noise, if there is some noise, it will be some additive noise will come. Okay, so this is a regular analog communication system. Then the fundamental issue that this low pass filtering will give you back the original waveform lies within this exact carrier what you are having at the receiver. So this is the receiver side, this is the receiver side RX side, and this is the transmitter side, so TX. So, but your channel can be really long channel, like it can be transatlantic channel, it can be around the entire world, it can be like transplanetary channel, wireless channel, different kind of channels. So it is not at all expected that your receiver will have information about the transmitter oscillator. So this is coming from some oscillator, isn't it? And there is some local oscillator here. So this is a local oscillator. There is no guarantee that this will have same value. Now, of course, if suppose you know somehow the frequency, but phase will not be exact. So you will get some phase with it. And if you get some phase with it, you will see that after low pass filtering, what you will get real of UT e to the power I phi, that you will get. So basically you will get UT cos phi. If there is some quadrature thing, then you will get say U real cos phi plus minus U imaginary sin phi. That kind of thing you will get. So you will not get the original signal even if there is some phi. And you know that this frequency is pretty high. So if FC is a gigahertz, you can understand that even if there is some error in the even if there is some delay, and if you don't know that delay exactly, a little small error in that timing will lead you to a large error in the phase, and with phase this will decay pretty fast. So that thing will be this same carrier and phase issue will come in the digital communication system. Let us take the QAM DSB quadrature carrier, and this is also like suppressed carrier. There is no carrier. One method what is applied or what is adopted by this analog communication people is that you send some pilot carrier, like amplitude modulation. In amplitude modulation you send a pilot carrier. So over there what happens that this XT is not really this, but also there is some carrier, pure carrier signal. such that at the receiver what you do, you can take a bandpass, like narrowband bandpass filter, and that can extract the carrier itself, and that can be used for demodulation. That is what in analog communication you do, right? So if you have some pilot carrier, then what you do, like from the channel the signal is coming, this is the channel, then what you do, you pass it through a very narrow pass filter, narrow pass band pass filter, narrow band pass filter, and that will extract your original waveform, that is some a cos 2 pi fct of that form, or e to the power I 2 pi fct. I can write both the quadratures. Then what you can do, you can multiply that with this, with an adequate gain. I'm not writing the gain, and then you can do LPF. So this is one approach, of course, this pilot carrier. But pilot carrier requires more energy, because that was like something which is not carrying any information. Okay, this problem is even severe with like quadrature amplitude modulation, for example. So in quadrature amplitude modulation, the diagram is similar, because this UT, whatever processing is done before that. So like using the matched filter and all. Now what you do, okay, I'm drawing the structure again. So you have the UT, which is basically summation UK P T minus KT. And this K can run from say minus infinity to infinity, or some 0 to n. It depends on what what is the chunk of data you want to transmit simultaneously. I can write 0 to n or something like that. Then what you are doing, you are multiplying this with the carrier wave e to the power I 2 pi fct. This is the quadrature carriers, and then you are taking the real part of it, because you are sending through a real channel, and you are again receiving at the side, and here you are multiplying again with this, like with e to the power minus I 2 pi fct plus say some phi t. Phi can be also time varying. It can be time varying also. If so, then what will happen? Then you are passing it through the matched filter and sampling it. KT. So what you are expecting, your so-called RKT, what you are getting, for you expect that this RKT should be your UK. So your expectation, and even with noise, your expectation is RKT is equal to UK plus NK. NK I can get rid of using detection theory, you know. The method we have already discussed, with some probability of error, of course. However, how do I know that this factor is UK? If there is some phi t here, so what will happen? Here you have seen that there will be some UT to the power I phi, so that will be there. You are doing it matched filtering, so matched filtering will take away the intersymbol interference definitely. You will get, if you do sampling, you will get definitely the factor UK, but the corresponding e to the power I phi will also be there, and in general UK is complex, isn't it? So this RKT will become, RKT is also complex for a QAM, so it will become e to the power I phi KT into UK. That factor will come. So if you look at the constellation, you will see that two factors will happen. Suppose you are taking some, say, QPSK. So this is your symbols in the like two dimensional complex plane plotting, you can say this is a QPSK. QPSK is also QAM. So what will happen? Suppose this signal has been sent. Now you are receiving it, but it is having some rotation with this. That is I phi KT. So suppose phi KT is positive, so it will have some rotation with this. And then you are adding the noise. So noise is suppose like this. So you get something like this. This is what you are receiving. So now how do you know that what factor is coming from the phase distortion and what factor is coming from the noise? So that is difficult. And unless you have some extra carrier, there is no way you can know this exactly. So there are different approaches to solve this problem. So before going to the generic like MAP or ML method, what I want to show you that we can get rid of this phase. We can know about this phase, say phi kt. If you have not a pilot carrier but some pilot symbols, if you have some pilot symbols, known symbols, which is used for synchronization. So I will basically take help of the characteristics of the noise and apply law of large number over there to get the phase, the error in phase. And if you can get the phase, if the frequency is correct, then getting the sampling time is not a problem. So we will talk about that in the next part when we will discuss about the phase locked loop. But before that, let me show you that in digital communication specifically, you do not need really pilot carrier. Rather, some pilot symbols, some initial symbols which are known to the receiver will give you the phase information. Let me show you. So what I am doing, suppose I know that the receiver knows that initially I am sending some known symbols. So in your constellation, this is the complex plane constellation of QAM. So QAM, suppose there is some symbols. We have taken QPSK, that is also like set of symbols. That is also fine. Or I can take some more, say this one, okay, this one and this one, and say this one. So these are my symbols. So on total 9. So I can say this is 9 QAM. So let us name them, say U1, U2, U3, U4, U5, U6, U7, U8, U9. So these are the 9 symbols. I am naming them. Now let us assume that the transmitter is sending only, say U2, 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 U1, say U1 up to say 30 times, say U2 say 20 times, something like that. This is known, suppose U9 some 20 times. Then what will happen? My receiver is expecting these signals, and this is suppose some standard. Now what the receiver is seeing that there will be some, and suppose that within this time limit or some considerable time duration, the phase is not changing much. The phase phi t is suppose very slowly varying or as if constant within that time interval. Okay, it has to be very slowly varying. If it's slowly varying, you have to resynchronize every time it is varying too much. Okay, suppose it is constant. So if phi is constant, then your received signal RKT, and if the the sampling is right, then RKT is UK e to the power I5 plus NK. This is what is received. This is from the constant phase error, and this is the noise. So what I am getting when I am receiving all U2s, I know, I already expect that something will come around this U2. This is your U2. But what is coming? It is coming that there will be some phase error. So this is your UK I5. So phi degree, like phi angle counterclockwise, and then the noise. So the first symbol is arriving here. Say this is 1. R1 you can say. The second symbol is again U2. So same, but then the noise is something else. So this is a 2, this is 3, this is 4. You are getting the clue, right? Where I am leading to. This is 5. So this is a complex noise. So it will have around, and this is Gaussian around this. So the kernel is 2-dimensional kernel. So you will get all the points like this, 6, 7, 8, 9, 10, up to say 20. So now what I will do, I will basically receive all those 20 symbols and take average, the sample average. So if you take sample average of that, so summation R KT for k is equal to say 1 to 20. So what you are getting, you are basically getting summation, and then you are averaging out by 1 by 20 say. So you are getting 1 by 20 summation U2 e to the power I5 plus 1 by 20 summation NK k is equal to 1 to 20. So this is what, here you can apply law of large number. So you are averaging out a zero mean Gaussian random variable or random vector here, or complex random variable here. So it will give you 0 plus I0. And what it gives you? This gives you simply u2 e to the power I5, because this value is constant for all 20 iterations. So this k is equal to 1 to 20, it will just cancel out, it will be this. So simply your average, which is say R average from 1 to 20, that will simply give this. So from here you can get phi. Phi will be basically like arg of R average 1 to 20 divided by u2. Knowing this, you will get the fetch. So if you want to like convince more, you then send u1, get the average like 5 value, send u9, get the 5 value and compare. If they are same, you have confidence that this is fine. Actually sending one symbol is fine for some time, such that the noise, like you can apply law of large number and noise cancels out to be 0. The sample mean becomes the expectation, which is 0. Then you can get the fetch. This method is called basically the carrier, decision directed carrier recovery, you can say. Decision means you are sending the symbol and that symbol is decided, detected. So this is called the decision directed carrier recovery. So this is one of the technique, but whether we can rely on this, because this also needs the the sampling time to be recovered separately. So next, but you get the idea that for what can be done for knowing the fetch. So next I am starting the quintessential circuit, you can say, the phase lock loop or PLL. So without PLL, communication, be it analog or digital communication, it is impossible. Amplitude modulation is fine, but other than that, these kind of coherent detection, coherent demodulation, those things are not possible. So this is essentially analog communication topic. Nevertheless, for the sake of completion, I don't know whether it has been taught in analog communication or not, so I am covering it. Okay. So this phase locked loop, and after phase locked loop, I will talk about the so-called estimation theory, where you can estimate a random process in presence of another random process. Actually, your Wiener filtering or Kalman filtering, those things fall within that scope. But right now, I will not have enough time to cover all of these Wiener filtering and Kalman filtering or particle filtering. Those are the filterings. But I will give you the names such that if you want in future, if you take some course on statistical like signal processing or statistical learning theory, you can read them. So I'm starting with phase locked loop. Now phase locked loop can be understood from different ways. One is control theory way, like representing the phase loop in terms of the Laplace variable and writing the transfer function and discussing the stability and all. But that is not that intuitive. So what I'm doing, I'm taking the intuitive approach, basically the analog communication, the Carlson book approach, you can say, in the time domain, such that we can understand that what exactly is happening. Okay. So our job at the receiver, so phase locked loop is a device at the receiver. So suppose some signal is coming. That signal xt is a band pass signal, or like pass band signal, I can say. So this signal is coming. Now you have a local oscillator, say voltage controlled oscillator. Probably you have learned this name in your analog circuit course, voltage controlled oscillator, where the input is some voltage and output phase, output instantaneous angle is controlled by that, or phase is controlled by that. So this voltage controlled oscillator is generating some signal which is of the form, say, a sine 2 pi fct, something like that. So what I want, there can be some phase also. What I want that this particular signal should have the same frequency as the input signal and same phase as the input signal. And let us assume that the input signal is basically some double sideband type of signal or amplitude modulated kind of signal, such that the frequency does not change with modulation, amplitude can change. Or it can be some passband signal. Passband signal, we know that it's like the frequency is basically deviating around some center frequency. Okay, there can be a continuous spectrum. Nevertheless, you can write that always a baseband passband signal in this form. So you can write that as some AC cos 2 pi fct plus phi t. In this form always you can write, such that your instantaneous frequency will be fc plus phi dot t. That will be your instantaneous frequency, and that frequency can change around that like some in between frequency. So this is like this kind of band. This is one band and this is another band. So this band point is say fc, this is minus fc, and there can be a continuous spectrum around that. So I want this to follow this. So I want this to match this, the frequency and phase. So to have that, basically first we have to understand that what is a phase comparator. How can you compare phases of two signals? So this is coming from the basic trigonometric identity of say, so sin A cos B, for example. So we know that sin A cos B is equal to sin A plus B, yeah, with a factor of half, plus sin A minus B. Now imagine that these angles are having of this form and their frequencies are similar. So this plus A plus B is basically a passband signal, similarly having very high frequency, and this will have some phase, or even if there is some variation in the frequency, it will have a very low frequency component. So some low pass filter will give you this sin A minus B part. So I am showing you that exact operation. So suppose you have some signal which is say AC cos phi theta ct. This is your signal, this is the angle, and you are multiplying it with some say AV sin phi ct, phi vt say. So what you will get? You will get half into sin theta ct plus theta vt into plus sin theta ct minus theta vt. So if you pass it through, so this signal is essentially half AC AV sin theta ct plus theta vt by 2 plus sin theta ct minus theta vt, sorry, theta vt minus theta ct, say this is sin, that is cos, yeah, by 2. So this is what the structure is like. So if you pass it through some suitable low pass filter, this will get rid of this. So what you will get? You will get half AC AV sin VT minus CT by 2. And our expectation is that if they are close, then this entire angle is very small. Then this you can get rid of sin, because sin epsilon is equal to epsilon in that format. Okay. So I can write actually from here that your theta Vt is equal to theta Ct minus epsilon t. So if so, then your yeah, or the other way around. So I can write it in terms of no, it's fine. So no, it is plus, say. So then theta Vt minus theta Ct is basically half into AC into AV sin epsilon t in this format. Okay. So assume, and if epsilon t is small, then you can get directly the phase difference from there. So with this understanding that a multiplier followed by a low pass filter, that can give you some idea about the phase, at least a sign functional of the phase. Then what we can do, we can basically assume that the local oscillator at the receiver, that is having some frequency over which it is oscillating, that frequency is close to the incoming frequency in some sense, and I am starting with some modulated signal, say, which is having a fixed carrier frequency. Then it can actually vary a little bit as well. So let us assume, I am taking the simplest assumption to show you that how it works. Then you can relax the stuff, it will still work. So the rigorous proof will be of course in the frequency domain, in the Laplace domain, but I am not going there. So let us assume that the carrier angle is basically this, 2 pi fct plus phi t. This is the incoming phase. Okay. In general, it can be a function of time. So this is the representation of any arbitrary band arbitrary passband signal. Okay. And what you are doing, you are having this signal incoming. So this is, let us take the amplitude of AC to be 2. So let us say AC is equal to 2. So you are getting 2 cos theta ct. That is what is coming. Now what you are doing phase detection in that way, multiplying it with our VCO output. So our voltage controlled oscillator is giving you some output which is a sine theta vt. Okay, and this theta vt is having this structure. Suppose theta vt is equal to 2 pi ft plus phi vt, and this ft may not be equal to fct, say fvt. So I can write this fvt is equal to fv is equal to say fc minus delta f. So there is a little variation, it may not be exact. Okay, and this is at at the so this is voltage controlled. So suppose this input is yt, so at yt is equal to 0. So when the controlling voltage or the bias, this you can say bias of the circuit, when the bias is 0, then fv is equal to fc minus delta f. But this will control, like the phase will depend on this. I'll tell you how. So now, if so, then your basically how this phase will how this voltage control oscillator will work. This will work as a phase modulated system. So your phase phi vt, this will have this kind of structure. Say some 2 pi kv integral 0 to t y tau t tau. This kind of structure. Okay. So you are integrating within the phase. This is like a phase modulator. Then this, if you do low pass filtering, what you are expecting? You are expecting that it will have some, we will do that analysis, it will have some form. So some RT suppose. Then you have some gain, some Ka, and I am saying that that output is your Yt. So Yt is basically Ka into RT. So this is called the loop gain, Ka. This is called the loop filter. And this is called the voltage control oscillator. So this entire thing is called the phase locked loop, and this will essentially show you that this voltage control oscillator output will lock its frequency and phase with the input signal. I'm showing you that. Okay. So this came in from your frequency or phase modulation understanding. This is called this is not phase, this is actually frequency modulated, isn't it? Phase modulation is when it is multiplied with the phase is directly multiplied with this. This is a frequency modulation. Frequency modulation system. So this is called the frequency deviation. So now let us analyze the error phase for the pattern. So your error phase is basically ET is theta ct minus theta vt for example, or theta vt minus theta ct. What did I write? Yeah, theta vt minus theta ct. So that is equal to theta vt is equal to 2 pi fct. Okay, I can make it plus delta f. No, nothing changes. So 2 pi fct to have a structure like this, plus 2 pi delta ft plus 5 vt minus 2 pi fct minus 5t. Okay, so this minus this, that is what your error is. Then that is equal to 2 pi fct cancels out. So you will have 2 pi delta ft plus 5 vt minus 5t. Okay. So what you can do, you can now what is 5 vt? 5 vt we know this. So to get in terms of y, what I can do, I can take derivative. So differentiating, I'll get epsilon dot t is equal to 2 pi delta f, assuming delta f is a constant, plus 5v dot t minus 5 dot t. Now I'll do some assumption that for the time being, assume for the time being that phi t is equal to a constant. So phi t means basically the phase of the incoming signal. So it is not arbitrary passband signal, it is basically some amplitude modulation kind of signal, such that like within the phase there is no other information, there is no deviation actually. So the inside angle is constant, whatever is happening in the amplitude, and that is a reasonable assumption, because so this says that this assumption means that the signal is not arbitrary bandpass, arbitrary passband, rather it's DSB type, DSB or amplitude modulation type. So your QAM is also DSB type, so that matches with our digital communication expectation. Okay, so then your phi dot t is equal to 0. So our like equation is now delta t is epsilon dot t is equal to 2 pi delta f plus 5v dot t. And what is 5v dot t? From here we know that 5v dot t is equal to 2 pi kv yt. So I am writing that here. So this is equal to 2 pi delta f plus 2 pi kv yt. And what is yt? Yt is equal to ka into rt. So 2 pi delta f plus kv into ka into rt. Now what is rt? RT is basically output of the low pass filter. So what do I expect over there? Output of the low pass filter. Output we are expecting half AC AV. Here AC is equal to 2, I am assuming, and AV is equal to 1. So that thing is 1. Sine epsilon t. So my YT is basically sine epsilon t. So this will give me, and let us say KCKV is equal to some K, some loop gain you can say. So I can write it 1 by 2 pi epsilon dot t is equal to delta f plus k into rt is equal to sine epsilon t. So this is the form you are getting. So I can take this side, I can write like 1 by 2 pi k epsilon dot t minus sine epsilon t is equal to delta f by k. So this is the dynamical system of the loop. So this is the dynamical system of the PLL. Now what I will do, I will show you, I will discuss that what will be the operating point if suppose if it attains some steady state. So I'm expecting that it will lock the frequency and the phase. So it will definitely attain some steady state. So at the steady state, what will happen? So epsilon t will become constant. So let us start from the steady state. So let us assume, let us analyze the steady state first. So at steady state, if it attains, then epsilon t will be some epsilon ss steady state. Then your epsilon t dot will be 0. So put that here. Then you will get that minus sine epsilon t, epsilon ss will be equal to delta f by k, or epsilon ss will be minus sine inverse delta f by k. So you can clearly see that the phase error which is obtained from the loop. So the loop is here. So what you are getting here, RT is basically like sine epsilon t. This is sine epsilon t. So if epsilon t is small, this R is basically giving you the error. So what RT you are getting delta f by k. So you have to make delta f by k small. Now delta f is characteristics of the VCO. So how the VCO frequency can fluctuate. So what you can control, you can definitely control k, because k is equal to Ka into Kv. Kv is the internal frequency deviation and k is the loop gain. So you can change the loop gain, you can increase Ka to make delta f by k very small, such that that this epsilon ss becomes very small or close to 0. So the condition is that, so at that, so what will be like yss will be definitely Ka into sine of epsilon ss, so which is equal to Ka into delta f by k, or I can write delta f by kv. That is what yss will be. Yss is this, the steady state. And then what will be your VCO output? So VCO output, say VSS I can write. This is the VCO output. This will be basically some sine of 2 pi fct plus the phase. Wait a minute. Yeah, it will finally reach to that same phase phi. So some phi 0 minus epsilon ss. It will reach there. So my everything will be fantastic if delta f by k is very small, close to 0 basically. Then VSS locks with incoming signal, with the incoming signal. Say this 2 cos 2 pi fct plus phi 0. So our design parameter is essentially k has to be k, which is equal to Ka Kv. It has to be greater than delta f. So you have to make this Ka, which is your design parameter, greater than delta f by Kv. This delta f by Kv is basically a parameter of the VCO. It is not always in your control. You can design some VCO, but it is not always in your control. This will have some value, but your Ka, this is your loop gain. This you can increase accordingly, such that your epsilon ss is very small. Now, interesting thing will be that if we can show that what will happen to the dynamics of the error when the value is small. So if this delta f by k is very small, say close to 0, then your epsilon ss is also close to 0. Say at some time, after say time t0, then epsilon t is small. If so, then the nonlinear equation sin epsilon t will become close to epsilon t. Then I can take the differential equation and I can solve it easily. So my corresponding differential equation will be from here, say 1 by 2 pi k epsilon dot t. Epsilon dot t, like how fast it will decay, minus epsilon t is equal to, this is 0 approximately. So what will be the dynamics? The dynamics will be Et. This is a like first order differential equation we know. So this will be equal to some epsilon t0 e to the power minus some 2 pi k into t minus t0 of this form. So where this 1 by 2 pi k is basically the time period of this system. This is like the time period, time constant you can say. So as long as this 1 by 2 pi k like your incoming as long as this phi t varies slowly in compared to the varying slowly in comparison of 1 by 2 pi k, then this locking mechanism will work, then the PLL will work. Okay, and if this PLL works, if you can compute that FC exactly, then you can compute the clock synchronization as well, because what is clock? Clock is basically, suppose your FC is some 1 by some TC, okay, that is like one wave, and this is suppose the time period for one symbol. So you have many like the sin FCT that fits in for a longer time. So this is a time t, this is TS, say this is for one symbol. I'm writing t because kt is what the sampling point is in the after the matched filter. Then we know that if we know that this t by 1 by f or fct, if fct is equal to some large number, say some L, which can be of the order of say 10 to the power 4 or something, if this is known, this is normally known from the design. So then knowing FC and knowing phase, you can exactly know that when the signal, incoming signal in the pass band is crossing, is 0 crossing 10 to the power 4 times. So you can have to have a counter over there. So your signal which is coming, you have some 0 crossing, and at every 0 crossing you start some like some Smith trigger, something such that it can give you a clock. And that clock you run some counter, that counter can, if you are computing 0 crossing, you have to basically go for 2 into 10 to the power 4. So counter will count for 2 into 10 to the power 4, and after that you know that is the sampling time. So with a digital circuit at that frequency, at close to that clock of FC, you can structure your clock for the matched filter receiver. So that can be computed if your phase locked loop works fine. But of course PLL is not the end of the story. There are more things. For example, Costa's loop. So this is more famous. This works in quadrature, and it has double the sensitivity of a PLL. I'm not going there. You can read it. This is beyond the scope at this point. But what I will do, I will next tell you the generic philosophy regarding the estimation of random process in presence of other random parameters. So to pose it in the same spirit of your detection theory. So in detection theory, you have seen that you are basically computing the likelihood function of your continuous random variable R, which is the received signal. after the decomposition and all. But the parameter set is finite or countable. So the parameter set is basically those symbols. The symbol for a QM set is very much finite. So you are doing for that. But right now, when your unknown is not the symbol, rather the phase and the timing delay. So I can write in a generic form that suppose your this is the general estimation theory. So what you are getting, you are sending the signal, say xt, and this is your channel. So what happens, this xt is what? Xt is basically a real of some ut e to the power I 2 pi fct. This is your passband channel, real channel. Now what you are receiving here, you are receiving some delayed and some phase distorted form. So the RT which you are getting there is basically, I should not write R, I said write Y or something, YT. R is after the masked filter. I am writing here only. So this is YT. So Y is nothing but real form of, you can say that U t minus tau, some delay, and e to the power I phi, some phase also, and some noise. So this is say baseband noise. This into e to the power I 2 pi fct. This is what is received eventually, and your demodulation will take out this e to the power I 2 pi fct form. The remaining thing will be there. So this I can write as some x, and when t, and you have two parameters, those are phi and tau, the delay and phase, and the noise. I can write this parameter space to be some theta. So this is the parameter, suppose. I can take some other symbol. Theta is also used for angle. Let us take some symbol like xi. So which is basically the two like random parameters, say phi and tau. Then I can write in generic form yt to be some x function of t but with parameter xi. This is random parameter. And this is noise. This random parameter, you can see clearly that both time and phase, both are real numbers. So this is a real vector. You have two random variables, both are continuous random variables. This is having a finite support, this is infinite support, but both are say delay, so like positive infinity support, and this is 0 to 2 pi support, but that's fine. But otherwise they are real, so they are continuous. So in this setup where x is very much like x is not only random originally, but also the parameter on which it is dependent, on which it is having this kind of dependence, is also random, and that is continuous random. So what I can do, I can now from here you can have the expansion. Expansion is basically masked filtering. So after masked filtering and sampling, what you can get, suppose you sample it n times. So you will get some n vector. So after masked filtering, you are getting some r. That r vector is basically r1, r2, rn. So this is the vector you are getting. This is for some time duration of capital NT. For that you are getting this. That is n dimensional, right? Then what I can find out? I can find out the joint PDF. The joint PDF, conditional PDF of R conditioned on xi. So that I can write as f of R given xi. So you can compute this is likelihood, but you can compute the a posteriori as well. F of xi given R, because that is what I want to compute, right? MAP will be maximization of this. This can be computed from the Bayes rule. provided you know the prior distribution of xi. So you can get now the simple relationship like the conditions. So for MAP, you basically maximize argmax f xi given r, and for ML means when you assume that the prior is equiprobable, you do argmax of f r given xi. So this is like that, and here this analysis has to be performed over all values of your xi which is continuous. Xi is basically time and phase, they are continuous. So for every value it has to be computed, and that is quite difficult, like even analytically, and then using circuit. So those Wiener filter, Kalman filter, particle filter, those concepts needs to be understood before solving this MAP and ML problem, because the search space is uncountably infinite, real number, contrary to the detection theory. So with this, I'm stopping on this carrier recovery and synchronization issues, but this is one of the key essential component of the entire digital communication system. Without this, nothing will work. Okay. After this, I'm stopping here. After this, our job is to go back to information theory, because right now, after detection, we can model the channel in a different way. So we'll channel in a probabilistic way and information theoretic way. So our rest of the classes, some 8 classes I'll take, that will be to understand the channel in an information theoretic way, and then how to infuse some redundancy in the input symbols, some extra bits, such that you can get rid of the errors which is coming from the detection, which is basically coming from the noise of the channel, and your detection theory cannot resolve it, but those error control codes can resolve it. So those will be our last final thing. Okay, so till then, bye.